Hello dear supervisors, my name is Alimzhan, and today my groupmate Zhan and I gonna present you our capstone project called Mobile Robot Motion Planning and Control with Obstacle Avoidance using Model Predictive Control. This capstone project is written under supervision of Dr. Almaz. Regarding the content of the presentation, we're going to start with objectives and possible application of our capstone project. Then we're going to recap the theory and results of the first semester. After that, we will continue with improvements which we made during the second semester and demonstrate you the simulations with the tracks we have built. In the end, we're going to conclude our work and shortly discuss the possible future work. The objectives of capstone project at first was to learn the control and optimization theory, learn wheeled robots kinematics and dynamics, and learn how to use Matlab Acado toolkit and Webot simulator. As we have learned that, the next objective was to create motion planning algorithms, implement these algorithms on different tracks, and in the end add feature in terms of obstacle avoidance. On this slide you can see a skid steer loader, which can be used for different purposes, such as cleaning the snow in the winter, cleaning some places from soil and rocks, or load some weights. And since the kinematics or four-wheel skid steer mobile robot used in our project is similar to the kinematics of this skid steer loader, in theory this loader can be automated since most of the tasks it's implemented are repetitive.
In this project, we are using Model Predictive Control to control a mobile skid-steered robot. Model Predictive Control, or MPC, is a process control method which plans control actions for a predefined limited number of steps into the future. It does this relying on the system's dynamic model and cost function that is minimized. As it plans for the future, it can anticipate future events and modify its control actions accordingly. Moreover, it generates controls that optimize system's future state. So each step is optimal in optimizing the state in the long run, not just the immediate outcome. In principle, Model Predictive Control minimizes the cost function over a limited prediction horizon by solving optimal control problem until that horizon. As a result, MPC calculates a plan of control actions that collectively minimize the cost at finite horizon. This approach allows MPC to optimize, taking system's future evolution into account, and also to anticipate future events like proximity to obstacles and modify its plan. And all the while, it also avoids computationally heavy tasks involved in infinite horizon problems. And since the model cannot be perfectly accurate, only first control step is applied, and the current state that results from applying that control is measured and passed as feedback to the controller. On the next step, MPC takes measured state as a starting state and solves the problem again and generates a new plan, starting from that measured state. The diagram here illustrates the process. Here YK and UK are system state and control action at instance K, respectively. Yref is a reference or target state, and cost function is on the right, which is least square sum minimization, or geometrically minimizes the distance between reference state and current state. So MPC samples yk and uk at instance k, which at current instance k, and minimizes the cost function over a period from k to k plus n, where n is a prediction horizon, or number of steps which the MPC controller predicts for the system. It solves the problem and generates UK, or control actions, that will drive the cost functions towards the target, and also generates target states or system states that it expects to obtain by applying all of these controls.
On this slide you can see the improvements we have made during second semester, and if in the first semester our algorithm was able to run the motion from the initial point to some reference point, now it's able to create new reference point every time step according to its trajectory. So we have created the algorithms both in time and spatial domains, and these algorithms can be applied for different tracks, such as a circle, 8, or complex track. All these tracks were constructed in the bot simulator, and in the end we added the ability of obstacle avoidance for our algorithms. All of the algorithms were successfully implemented in the Akada toolkit and simulated in the bot simulator. Now we can see mobile robot kinematic model used in our project. And from the first system of equations, you can notice that velocity of the mobile robot in x and y direction and angular velocity depends on velocities of left and right motors and some constant coefficients, alpha L and alpha R, which are correction factors, and x ICR and y ICR, which are instantaneous center of rotations. Robot's motion described in global coordinates can be seen from the third system of equations. And in general, displacement in x direction is equal to vx multiplied by k sine theta plus vy multiplied by sine theta, and displacement in y direction is equal to vx multiplied by sine theta plus vy multiplied by cosine theta. However, with the help of non-harmonic constraint for the skid-steered robot, we replace vy with negative x ICR multiplied by theta dot, where theta dot is the angular velocity. And on the third system of equation, you can see already upgraded kinematic model. The first algorithm is circle track algorithm. On the slide you can see the formula trajectory and screenshots from Akada and Ubots. The code of the circle track algorithm is quite similar to what we used in the previous semester, however with some upgrades. We added angular velocity to differential state. Time step is 100 milliseconds. Here you can see the constant coefficients we have discussed before, and kinematic model of the mobile robot, and differential equations depends on the global coordinates. Prediction horizon is 50 steps, and here are limits of velocity and accelerations, which were taken according to datasheet in the mobile robot. We have circle of radius 5 meters, and as we have told before, if in previous semester we have generated the path from one point to another, this algorithm generates new point every time step. So here we can see the trajectory, the circle track, and calculations of angular velocity. And if we simulate it, we can see the red circle is the track, blue triangle is the mobile robot, and blue path is the path of the mobile robot. So the simulation in Webots, we have a controller also written in Matlab for Webots. Here we take the current position and rotation of the robot and input it in the previously constructed controller. As you can see, mobile robot quite accurately follow the path. The next algorithm is 8-track. It's called 8 because of the form of number 8. Here you can see the formula of the x and y coordinates, the trajectory, and screenshots of the simulations in Matlab and Webots. The code of the 8-track algorithm is similar to circle track algorithm, except we differently calculate x and y coordinates, the trajectory, and angular velocity. And also some of the coefficients also differs because of the different track. Here you can see red dashed line is the trajectory, reference trajectory. Blue triangle is the mobile robot, and the blue line is the path of the robot. Here we can see that on the straight line, mobile robot accelerates, and on the turnovers tries to decrease its speed, finding the optimal velocity and acceleration in order to fit the trajectory line. And here's a robot simulation and a constructed road following the 8 with the Pioneer 380 mobile robot placed in the position of 0, 0. Here we can notice a similar pattern in the velocity and acceleration of the mobile robot. Tries to find optimal velocity and acceleration for straight lines and turnovers in order to reduce the difference with the reference path, and both trying to go through it with the minimum time. Next track is the upgraded version of the previous track. Here is mobile robot will be able to avoid the obstacles. Regarding the change in the code, we have added so-called soft constraints in the objective function. Here you can see the formula. As you can see, each equation is the separate obstacle. 1.21 is the x position of the obstacle, and 2.3 is the y position of the obstacle. Radius of the obstacle is 0.5. In fact, the radius of the obstacle is 0.2. However, we add additional 30 centimeters as the size of the mobile robot. When mobile robot approaches the obstacle, value of the obstacle increases, so controller tries to find the way where this value will be lower. Now we're going to simulate. So again, red dashed line is the reference trajectory, red circles is obstacle, blue triangle is mobile robot, and blue line is the path of the robot. Now you can see the cyan colored line in front of the triangle is the prediction horizon. So mobile robot quite accurately follows the path and avoids the obstacles. Now we will see it in Whipple Simulator. Here you can also see how mobile robot nicely avoids the obstacles and returns to its reference path.
In addition to time domain formulation, spatial domain formulation was also developed. This kind of formulation is also called path following. In path following, position of mobile robot is defined in frame of virtual vehicle that moves along a predefined path. So position of robot is now defined by error coordinates xe, ye, and theta e, which are decided by these expressions. Here, S is the path curvilinear abscissa, and C of S is curvature of the path, parameterized by S, or by arc length. On the diagram, moving frame is denoted by point P, and new axes are denoted by XC and YE. Previously, in time domain, the vehicle's movement was described in terms of world reference, which is point O here, and axis XW and YW. Now the reference is constantly moving along the predefined path, which is noted by this P, and position of the vehicle is always linked to that point P. So, and also point P is also, since point P is also moving, the whole system is now also defined by S, which is curvilinear abscissa of the path. Basically, the path now also works as an axis to describe the system's movement. With path following formulation, robot movement is now controlled by the curvatures applied to the controller. To obtain this curvature, path described by set of xy points in world frame is approximated with a cubic spline. Cubic spline approximates not y versus x function, it approximates x versus s and y versus s functions, s being the arc lengths of the path. So using this spline, curvature can now be computed using this formula and supplied to the controller, which then solves the uses this ordinary differential equation system that defines the model. The equations of this ODEs are here, which is xe, ye, and cte derivatives, and also one more to define the change in s, and which is the projection of the vehicle forward moving velocity onto the reference frame P, onto xe coordinate. With this formulation, the robot can be made to follow a path by simply setting the targets for error coordinates as 0 and target for velocity along the path to some velocity, some finite velocity. So with this target set, the robot will follow the path as it will try to minimize the deviation from the virtual vehicle position, which is always on the path, and actual robot's position, and also target a certain velocity along this path. Thus, the robot should be moving along the path with designated velocity, if possible. The final version of path following control is done on this complex track, both in Matlab and in VBot's simulator. The controller used here also has obstacle and border avoidance features, which is implemented using these terms incorporated into a cost function. These terms sharply increase the value of cost function if the robot approaches the obstacle, which position is defined by this ye obs, xe obs coordinates, and also radius of the obstacle plus radius of the car. Border avoidance is done in similar fashion, but instead of the ye obs and xe obs, now it's simply discouraged to deviate from the center of the path by simply including this term, so it does not have xe. It just increases in value if the robot approaches the border. Now I'm going to demonstrate how the system works in both Matlab and VBot's simulator. In Matlab, here is the code that defines the system model and obstacle avoidance terms. These terms and these ordinary differential equations. here that as described previously. And here's the cost function, which includes target velocity along the path and obstacle avoidance terms. And ds1 to 3 are these terms, which are error coordinates. So here's definition of cost function, which is minimize least square sum. And here are constraints on maximum velocity of the wheels and maximum acceleration of the wheels. So these are the this is the initial state. So all of the error coordinates are, and S coordinate is at 0. And here is a reference state, which is sets everything at 0. This is a reference, not state, it's a reference for the cost function. So everything is at 0 except the target velocity. And here are the weights for each of the cost functions terms. So here the controller is implemented. Oh, and also here's obstacle definitions. They are defined as a matrix. The first column and second column is XY position, and the third column is the radius of the obstacle. So now let's run the code. So here is the robot movement along the track. You can see how it avoids the obstacles. It can avoid multiple obstacles as it's constantly updating which obstacle to avoid. Well, we have only one term in the obstacle avoidance for obstacle avoidance, and so there is a function that constantly searches for the closest obstacle and sets it as the one obstacle it must avoid. So as you can see in Matlab, the robot tries to stay on the path as close as possible. And in absence of obstacles, the error is minimal. So now it arrived at the end, and the controller stopped, as there's a code that stops the controller if it reaches the end of the path. So here are control inputs that were generated throughout the operation of the controller, and here is the final trajectory. So the feedback to the system is also done completely online. It does not take any states from itself. It does this from the simulator, which is this. It gets this state sim, which is a simulator in time, simulates the robot motion in time domain. and the simulator is defined by the model used previously for trajectory tracking model. And all of these functions, this function computes the curvature, then the function splinify, which was here, it computes the cubic splines used here. Scan LBS, looks for closest obstacle, point to S function. This function implements golden section search to find closest point on the path. This is done to find the correct position on S currently. And reference to S changes the points defined in global coordinates into a reference frame of the virtual vehicle. And here span trajectory. This is used to visualize the trajectory that the controller plans to move. Now I'm going to showcase how the system works in a more comprehensive simulator, which is VBots. The robot starts moving, very similar to how it moved in the Matlab. The green spheres represent the planet trajectory of the robot. Now I would like to explain how the feedback loop works here. So first, the point to S function takes the current X and Y coordinates of the robot directly from the simulator and find the closest point on the path to it and outputs the S coordinate, which is a curvilinear abscissa of the path. Then, using this abscissa, it finds the error coordinates to pass as the initial state. So this is how the measurement here is done from the world frame to the frame of virtual vehicle. It is important to note that as the position is taken directly from the simulator, there is no localization error involved. So performance might be not ideal in case of noisy localization. Additionally, I would like to show that the system can be easily manipulated. For example, if I wanted to be offset from the center of the track, I can change the reference of y error to 1, and now it should follow the path slightly offset from the center. Oh yes, now it changes the direction. Now it tries to stay to the right of the center, or to the left of the center. So now, yes, it stays slightly to the left from the center of the track. In similar fashion, target velocity can be also changed. Let's set it to 0.5. So now it got very slow, and because of very short horizon it decided to go in different direction. Yeah, performance with such speed is not ideal, because a very short horizon it often follows not optimal paths. And the track itself is also easily modifiable. So by simply changing the set of XY points that the robot should follow. So let's change it to the 8 track, like this, and turn it on. So now it follows the 8 shape. Although it appears that it's slowed down in speed in order to maintain a low error. Thus, the path-following robot control was developed on Matlab with Arcado and tested in both Matlab and Vitbobs under ideal conditions. By ideal condition, I mean the perfect localization and perfect obstacle localization.
In conclusion, we want to state that all the initial objectives were achieved, and we have implemented trajectory tracking algorithm in time domain and path following algorithm in spatial domain. All the algorithms were simulated in Matlab and in Vitbob simulator, and we expanded our MPC controller with obstacle avoidance. In future work, we want to possibly write research paper on comparison of these two implementation techniques and possibly transfer the code of algorithms on real Pioneer 380 robot. We want to apologize for such long video because we want to show you all the simulations. Thank you for your attention.